Hello, my name is Donna Renemo, and on behalf of WindSim, we welcome you to the Bark Optimizer webinar series, or webinar today. The session will last 1 hour, and during the last 15 minutes of this session, we will address questions and answers, as many as we can. And we will ask, since all of you are muted to enhance this presentation, that you send your questions via the chat window, either to the host or to Klaus Vogstad, who will be providing this presentation today. And with that, I will turn this presentation and this discussion over to Mr. Vogstad.
Hello, I'm Klaus Vogstad. I work with wind resource assessment in Norway, and I'm using WindSim, and I'm developer of the Park Optimizer tool that we have found useful for extending the capabilities of WindSim. I will show you today what Park Optimizer offers. Park Optimizer is a post-processor for WindSim CFD results. It utilizes the results from WindSim and can calculate the IC standards, the constraints as defined by IC for wind turbine design. It can furthermore optimize the turbine layout in another way that than the existing tools are doing, by taking into considerations the IC constraints. So what we do with this tool is actually to try to take into account the quality of the wind or the IC constraints as early as possible in the project stage, rather than checking for those constraints later. The third thing, the fourth step we also do is to find the appropriate size of the project. And in order to do that, we introduce the criteria on the profitability and the risk of the project risk, and we will explore that relationship during the course of this presentation. So the goal of the Park Optimizer is to be able to design an IEC compliant layout that optimize the layout with respect to profitability, and also can minimize the project risk of the developer. So during the demonstration, I will show the Park Optimizer on a real case. And the case we have been working on, and that actually started the whole idea behind the Park Optimizer. We're using WindSim in our wind resource assessment in Norway because we deal with complex terrain. We also use industry standard tools like WindPro, but there was a gap there as we wanted to find out what is the appropriate size, or should be the appropriate size of the wind project, and also we wanted to improve on the optimization, and we had to take into account the complex flow in Norway, and wanted to avoid the most the worst quality of the wind within the site. So that's why we came up with mapping the IC exclusion areas before we started doing the optimization. So it comes in as a constraint during the optimization. We thought that was a better way of doing the project management or the project development. A little bit about this project, this case study that we will follow up. This case study, the project, it got a permit in, let's say, 1.5 years ago. It has a permit for up to 150 megawatts. It's located in medium complex terrain, and Park Optimizer has actually, or the predecessor of Park Optimizer, has been used on this project throughout this project development stage. So it was used as early as in 2009. The planned construction start is around 2014. So we're still working on this project and using Park Optimizer to determine the appropriate layout of the project and maximize the profitability. The challenge of this project, as with most projects in complex terrain, I believe, is to design a layout that is IEC compliant and that simultaneously maximize the profitability and reduce the project risk. And this is what we're going to demonstrate using the Park Optimizer tool throughout this presentation. I will switch over to the Park Optimizer tool. Let's start Park Optimizer. It is version 1.17 that we will start up. We are developing a new version of the improved version of the Park Optimizer tool, and I will come back to that later. The Park Optimizer tool can read WindSim project files directly. So if we check this button here, WindSim project, then we can go straight on to our project file, and it will automatically know, it will be able to read in all the files underlying the folder structure of a typical WindSim project. I can demonstrate this now by just loading in. And it will take a little while to load in the data. And Park Optimizer uses several data to be able to calculate shear, terrain inclination, flow inclination, and turbulence. Okay, so here is the WindSim files loaded in, and what is demonstrated here is just a terrain map of the terrain inclination in from the WindSim project. Another way and faster way, when you have worked on a project in Park Optimizer, is that you can load a Park Optimizer project file, and we will do that now in order to save some time. Just get a couple of warnings here because it loads layouts where there are some turbines on one of the edges. Okay, so now we have loaded a project file in Park Optimizer, and we have also loaded in the park area here. So what you can see here is the park area, and from now on we will only be interested in the park area and not the rest of the WindSim simulations. So here you can see the project just zoomed into the park area. We can show a wind resource map here of the project. So when we have loaded in the project, it is possible here also to just load in the wind resource map, the VRG file from WindSim, and you can also make your own calculations on the energy production by choosing an appropriate file or information on turbines. We will go over to the constraints now. The constraints are as defined by the IEC standard, and that represents the quality of the wind. The reasoning behind this is that we wanted actually to include these types of constraints as early as possible in the project development phase, because it provides some interesting information, and using CFD, much of the information is already there or can be extracted from the CFD results. That includes the flow inclination, that includes the shear, and that includes the turbulence. So what we do is to, first of all, we include the terrain inclination. That's not a real IC. That's not within the IC standard, but it's useful to include as well. We include the flow inclination, turbulence intensity as calculated by WindSim, shear, and then also extreme wind in order to get and we aggregate. We add these together and define as exclusion areas where you should not put turbines. So that's the gray areas you can see here. So once we have mapped all these wind conditions, we are ready to perform our layout optimization. I will talk a little bit more about the constraints. You can define the IC, the range yourself. I have added a little bit slack here in this case. And then let's say if we, for instance, are interested in the flow inclination only, we check this button and we can extract from the WindSim files the flow inclination. While this is computing now, as you can see on the status bar here, if we hover over each of these standards, you can see flow inclination will actually require some WindSim files, and that's the speed 2D SS or 2D speed 2D files from the various sectors involved. It will require the VCRT files, and it will require that from all the sectors. So these maps are actually are superimposed for all the sectors we consider. So in this case, we consider 12 sectors, and we make a total aggregated exclusion area for flow inclination that applies to the total of all sectors. In this case, there weren't a lot of problems with the vertical flow here. As you can see, there are some small gray areas here, but apart from that, it doesn't seem to be a very constraining problem for the layout. We could do similar for shear and terrain inclination and turbulence. So in order to save some time, I have already saved pre-computed extraction of those exclusion areas. So I will open that. And these are stored for your convenience as CSV file, because if you want to use other tools or need to use other tools to process these data, for instance, using GIS tools to display them and so on, then there's always some files and some formats that are, the CSV format is a convenient file format to work with. Okay, so here are all the different constraints superimposed into one big map. It is also possible to explore each sector, and you can also, instead of displaying a logical map here is whether the constraint is the IC standard is violated or not. You can explore further, let's say, the turbulence or the flow inclination in terms of absolute numbers, so you get a color map. That's also possible to do. It's also possible to add constraints by simply importing shapefiles, or you can make your own constraints. Let's say we can draw some constraints. Say if I wanted to impose an additional constraint here, that's feasible. And in many cases, this is what you have to do. It's not. There are always some constraints you have to add manually when you fine-tune a layout in a project. But this can be done either in this tool, or you can export maps and then continue the editing in your preferred tool. I'll explain a little bit more about the turbulence. Turbulence and extreme wind are two important criterions to classify the site. In our case, we have used we import turbulence intensity as it is calculated by WindSim, and then if the user has a file wants to include a wind measurement file, we can calibrate the turbulence intensity from WindSim with the data from wind measurements in terms of a TWS file, where the standard deviation of the wind is stated. Our tests against real data shows that it improves the results, but it should be also be taken care, because the placement of the measurement mast is, the results could be quite sensitive to the placement of the measurement masts. So this type of calculation uses the turbulence intensity files from WindSim, and also it uses the speed up with respect to wind speed, and also the change in wind direction when it extrapolates the wind data onto the whole park area. With extreme wind, we will not include in this presentation here, but because it's quite time consuming to extrapolate extreme wind, but we also did our test on that, and we use method of independent storms, has implemented that in the Park Optimizer tool, and we have a method for extrapolating the extreme wind onto the site. These results should also be taken with care, but we have also done tests on that, and if you actually run a WindSim model with boundary conditions that are at extreme wind speed, the reference speed, then you can actually achieve some better results. So we think that's a promising way forward. Okay, so now that we have mapped out the areas that are not suitable for wind resource or for putting turbines, we can move on to placing the turbines. Before we do that, I will just say that a layout optimization is actually a very difficult problem. This is due to the following three requirements. The minimum distance, there is a certain minimum distance required between each turbine. You have the wake deficit that will influence the total production as a function of how you position each turbine and the interdependency between these. And it is the effective turbulence that all these three, so to speak, constraints or interdependencies has the effect that one turbine, the way you put one turbine will affect how you can put all the other turbines. And when you place a lot of turbines in a large project, you have practically, let's say on a 200 times 300 cell grid, you have in practice an infinitely amount of possible combinations for a layout. So you have to find some smart search algorithm that can find the optimal placement. What we learned, we focused in the beginning. We focused a lot on wake deficit, the wake calculations. The minimum distance we managed to get a good algorithm on that actually guaranteed optimum. When we added the wake model, it was a bit more difficult to optimize. But we have also learned that the effective turbulence is much more constraining, in our opinion, than the wake loss. So the effective turbulence is also an absolute constraint, or at least is defined by the IC standard. So you have to be within the standard, and it turns out that we have managed to actually optimize with respect to the effective turbulence constraint in our model. And once you have included that, that will also help reduce the wake deficit, and the effective turbulence requires much more distances, or is much more constraining in our opinion in complex terrain than the desirable distance between turbines due to the wake losses. So I will now show the optimization window here. Here is where you can, I will come back to this, the number of turbines you can select for the optimization. But here is the minimum distance requirement. That's a requirement that we have been able to solve to guarantee optimum on. And then we add the wake effect, optimize with wake effect, and add effective turbulence as a constraint. And in doing so, we are able to obtain an IC compliant layout as part of the optimization. The way it is done now is that in most programs it is optimized, or one find a layout trying to minimize wake losses. But then afterwards, you have to check whether that layout is feasible using WASP engineering and Wind Assessment Tool. So we think it's better to include those IC standards from the beginning as part of the optimization, because if you have to adjust the optimization afterwards, well, then you're it's not really an optimal solution. Okay. A third, before we go on to explore the results, a third point is how many turbines should you put on the site? And that's a question that we will see later why we think this is important. But what we actually do in the optimization is to optimize with respect to one turbine. We then optimize with respect to 2 turbines, and then all the way up to the maximum number of turbines. So here you can see for the project all those possible project sizes that are optimized. This requires, of course, either a lot of patience or also an efficient and fast algorithm in order to do that. I can show one of these layouts. Let's say this is for layout with 65 turbines, which is the maximum. So here you can see the layout where the numbers represent the from the best turbine, or the most producing turbine is number 1, the next most producing turbine is number 2, etc., all the way up to 65. But we have a whole list of layouts here. So let's explore, for instance, layout with 47 turbines. Now I get just a warning here because some of the turbines are just on the border of the park area. So here you see a different layout, but that's just with 47 turbines. So why do we take all the bother to look at all these different project sizes? Well, if we now plot the total energy production for each of those, the total energy production for each layout, then we get this interesting picture. Here I have plotted the energy production on the red line, the energy production as a function of project size. That's the total energy production for the whole site. So as we increase energy production or increase the number of turbines, it will become increasingly more difficult to find good spots for the turbines, and moreover, the wakes will steal more energy from each other. So then you have a marginally decreasing, you have a convex curve here. It might be more easily displayed by plotting the marginal change in energy output per added turbine. So here you can see the first turbine has the highest production, or if you only made a site with one turbine, of course, you put it on the best spot. But as you have to squeeze in more and more turbines, you can see the production, the marginal increase in production, it drops. So the last turbine you squeeze in is down to at least, well, it's just 70% of the maximum producing turbine. So where should we stop? Should we stop at 60 turbines? Should we stop at 40? Or should we stop at 20 turbines? Or should we build the maximum size of the project? In order to analyze that, we can plot the profitability of the whole project if we include investment costs, if we include turbine costs, if we include all these various costs. Let's say I have plotted, I have just shown the equation here. An investment analysis will require, let's say, you have some fixed cost, the external road, grid connection, and so on. That does not depend on how many turbines you build. There is the variable cost in terms of the internal roads, cabling, foundation, and so on, and you have the turbine costs. And then it is the discounted cash flow, the revenues you get throughout the lifetime of the project. And that is composed of the prices, of course, the energy price and the subsidies. The subsidy that you might acquire. And then it is the energy production as a function of number of turbines. And then operational cost. So this equation here, where you plot the profitability as a function of the project size, and the project size, I mean the production, the energy production of the total project, it depends, of course, on how many turbines you squeeze in. We arrive at this interesting curve here. Now you need only to look at the blue curve, the thick blue line. Along the x-axis is the number of turbines, again, corresponding to the last graph I showed here. Let's see, here. And along the y-axis, you have the profitability of the project. So the more at first you have, of course, on fixed investment costs that you have to distribute on the production of the turbines. So as you increase the number of turbines, then of course you increase profitability up to a certain limit. And then it seems to just taper off and decline again after you reach a certain number of turbines. So that means that the turbines, after, let's say, 45 turbines, if you put in more than 45 turbines, those turbines will not generate enough revenues in order to pay for what they actually cost to build them. So an appropriate size here, I would think, is around 30 turbines, 30 to 35 turbines. So let's see how this is implemented in the park design tool. We have now a list of layouts. I have already done the optimization here, so you can get a list of layouts here. But let's move on to the economic optimization. You obtained the energy curve as I showed in the slides here as a functional number of turbines. And then here is the marginal change in energy production. So this is the energy output per added turbine, you can say. It is a little bit noisy, this curve, because we can't guarantee a perfect, exact, optimal solution for each layout. So there is a certain element of noise here. But with a better optimization algorithm and the one we have been able to implement in Park Optimizer 2.0, then this should be this curve should be smooth, and it should be a declining curve. Then I have put in costs and price figures here. So we have some fixed cost of the whole project. You have some turbine costs, and you have some cost per turbine for road and cables internally in Park. And then we have some prices, energy prices, I put 40 euros here, and some subsidy schemes. And these are considered in this way here. This is not to get a very precise, exact investment analysis. But you can actually, what you can do is actually just to take the results from the Park Optimizer, which is written to some files, and put it into your own spreadsheets in order to do that exactly. Now let's plot the profitability here, and as you can see here, we get a peak around between 30 and 40 turbines here in this case. Let's suppose if the turbine costs were a bit higher than 1 million euros per megawatt, let's say 20% higher, then you would see this optimum changes down towards around 20 turbines. We can change it back again, and this will be also the case with other parameters. So in this way, in a rough way, we can assess, okay, what is the appropriate size of this project, and we can return back to the layouts here and pick the layout that we think is the most appropriate for this project. So I pick 30 turbines as a layout. Okay, we can explore this layout a bit further now that we ended on an appropriate size. I have plotted here the wind resource map, and you can even include a background map if you want. Here I have included the constraints as well. So if I just uncheck the wind resource map, you will see these are the IC constraints, and here is the layout. It is even possible, once we have ended up on a layout, we can get a printout of the IC values for those specific turbine positions. So there is a reporting function here where, well, the first reporting function is that you can actually export this map to a KML file and include it in Google Earth. That was one of the pictures I showed in the start of the presentation, including also the constraints and the layout. You can also include, but what we will look at now is the IC constraints for layout. It will take a time to print this out, so I have already prepared one, but if you press this button, it will generate a report of the IC compliance for each turbine position. So let's have a look at that. Okay. It is just a plain text file, but as you can see here, the text file includes a set of turbines from 1 to 30. You have the position of the turbines, the height, and you have the wind speed in terms of A and K variable parameter, the mean wind speed, and the wind speed including the wake. terrain inclination, flow inclination, shear values, ambient turbulence, and effective turbulence. So here we can inspect the layout a bit further. I haven't included extreme wind speed here, but that can also be included if you have time enough to calculate that. So if we explore down here, we know that effective turbulence should be below 18% for class A site. And there are a couple of positions that violate that. Actually, I included a little bit slack when I put the IC limits here. But apart from that, you can see that actually this layout satisfied for mostly, well, roughly, all the IC standards. So it is an INC compliant layout. Now, a turbine manufacturer have, of course, much more detailed information about the turbine, so they might be tighter on the limits of the turbine, as they can do load calculations. But from the information we have access to is that we can at least compute the IC standard, and we know that also turbine manufacturers are using the effective turbulence as a first check before they eventually do some load calculations. You can explore for each turbine the different sectors and how they contribute to the IC compliance. This gives some indications. It should be taken with care. It should be compared maybe with other similar tools. We are doing these comparisons and we are trying to improve it because these are calculations based on safety results and also combined with wind measurements. But we get good results, and we also have presented some results at previous WindSim user meetings, and we are continuing to do our own internal test in order to be sure that these provides a good layouts that can be further analyzed. Okay, then I can maybe show a little bit of well, where the results end up here that I have showed here. The results ends up in a folder called opt-out, where you have different layouts. So let's say layout 30, for instance, we have adjusted the layouts with wake, so in several rounds. So let's say here, if you go to layout 30, it is in a format that can be easily read into WASP and to WindSim. So we have provided the two formats here. So here's layout 30 in a familiar format, and a similar one, OWS format, which is the WindSim format for the layout. So there's one of these layouts files for each for each project size, and a summary that you can, for instance, export into your spreadsheet, your financial spreadsheet. Is the energy curve. This is how this looks. So for turbine 1, the production was 9,400 megawatt hours. For turbine 2, 18,000, etc., and all down the way to 65 turbines in the layout. So when we finally arrived at a proper size of the project according to our financial assumptions, and when we have been able to make an IC compliant layout, then we have managed to make a profitable and IC compliant optimal layout. with respect to the project risk that I mentioned, if you look at this curve again, it has actually more important implications for the project risk. If you were to choose between developing 35 turbines or 55 turbines, which has approximately the same profitability, you will double the investment cost if you go for the 55 turbines alternative, as if you go for the 35 turbines alternative. And that will only have the effect of increasing your project risk and not really making the project more profitable. So I think to display these results has an even more importance when you do project financing and when you care about the project risk. So before, I can just conclude the presentation for Park Optimizer 117. I would just like to mention before I conclude the presentation that we have been working on improvements in Park Optimizer 2.0. We are expecting to release that before the end of the year, and we have had actually a breakthrough this summer by being able to find an algorithm that guarantees a global optimal solution that includes effector turbulence and that includes minimum distance, and will probably be a very good optimization also if you consider the wake loss. It will be a much faster optimization algorithm. It is not a trial and error or this evolutionary approach. It is actually an exact formal optimization technique that we have been able to adapt and fit to this particular problem. It can also provide alternative solutions by defining, let's say, if you can accept a 1% reduction, small reduction from the optimal production, you can actually get a wide range of different layouts that you would be preferable to the optimal alternative with respect to other considerations that does not that you're not able to include in a mathematical optimization. That might be aesthetic purposes, that might be some other aspects of visibility and so forth. And we are working to improve those ambient turbulence calculations with that is using the WindSim results and wind measurements, and to be updated and precise according to the latest amendments of the IEC standard. Okay, that concludes my presentation, and I give the word over to Donna.
Thank you very much, Klaus. So we have had some questions come in, and you will see them in your chat window. If you like, I could read the question to you, and we can address a couple of them. We have 15 minutes before we conclude today. So would you like me to read, or
Yes.
do you want to just, okay. So the
I saw some question here,
okay.
so I can take one.
Okay, good.
One of the last questions here was, does the optimizer calculate electrical losses and consider it in the financial analysis? No, the electrical losses is not included as part of the optimization. The reason for this is that the electrical losses is in the range of the absolute losses is in the range of 2 to 3% within the site, within the park. So we think it's too low to consider or to justify to consider it at this stage. For instance, if you take those electrical losses into account, let's say you extend or you have a longer distance between the turbines or a longer length of the cables, then let's say that will maybe increase the electrical losses by 10 to 20%. and 10 to 20% of 2% initially, that's down to some per mils. So that's the basic reason. But it is doable, it is feasible. It has not been a priority. Let's say. Another question. It sounds like the optimizer is complicated. Would WindSim be available to help? Yes, WindSim will be available to help for well, typical problems. There is a support for from WindSim. If there are some more tricky questions concerning the algorithms or some problems with the server or compatibility, then those questions will be handed over to me. Let's say there's a question here. Often turbines can be approved in conditions that exceed the IC standard. Is there any way to make an IC heat map or something that shows how far outside the IC standard each of the factors is, or a combination of all the factors is? Yes, there is. It is possible to study each sector independently. It is also possible to make a heat map, but for each sector and for each, and also the aggregate of all sectors. And you can also set the IC standard yourself. You can set the constraints as I did in this presentation. We know that turbine manufacturers has much more detailed information on the turbines and can be closer on the margins. We just follow the IC standard, and I think that's a starting point before one can do some fine tuning. But you can also actually do this at a very early stage in a project, and thereby avoid a lot of, let's say, problems or areas that are actually not really feasible for wind, that you should not spend a lot of time on, and maybe avoid a lot of cost dealing with landowners and dealing with authorities in areas where you should actually exclude these areas within the site from the beginning on. Another question here. What format should extreme wind constraints be in? Can WASP engineering results be used directly? For extreme wind, we have been, what we use is just pure time series, wind data time series, at 10 minutes interval. And in order to extrapolate extreme wind onto the whole park area, we are using data from WindSim. So it is explained. The method is explained in the help menu in Park Optimizer. I can actually show that now. Oops. Okay, I'll have to look into that. Yeah, if there should be any problems with the documentation, you can just contact me. But I don't know just what happened here now. But we use the method of independent storms, and it is documented in the documentation. We don't try to do anything wildly different from what the turbine manufacturers do. So we just listen to, in this case, NRK, how they actually were doing their extreme wind calculations, and try to represent that in our models.
So Klaus, we have time for one more question. There's one more that's come in. If you'd like to address that.
Yes, okay. The last one here, let's say. is the number of turbines limited by the project constraints or by the optimization model algorithm? The number of turbines is constrained by, both the project constraints, of course. If you have you can't put turbines outside the wind farm, the project area, and of course it is the three requirements: minimum distance, effective turbulence, and the weight loss. In particular, it is the effective turbulence that constrains how many turbines you can squeeze into the project. So we learned that we need more distances or more spacing between the turbines in order to satisfy the IT standards, which is quite strict than we were expecting earlier on.
Okay, we have one more that's come in. We have a few more moments left.
Yes, let's see. How can I determine which is the optimal rotor diameter for any given site using WindSim Optimizer? Well, that's a thing. We don't include that in optimization automatically. We look at. You can put in any type of turbine, and it will calculate the wind resource map, and you can perform the optimization. But you can only do that for, let's say, you have to select manually the turbine yourself. So we haven't expanded the model into that, into also choosing which is the best, which is the optimal rotor diameter for you. But what I would suggest for that, what we do is that we have some cost figures for each turbine, some typical cost estimates or prices, and then it's of course how much energy do you get per cost unit for the turbines, and that's what really constrains, or that's what we use to choose, get a rough list of turbines. Usually the most modern turbines are the ones that performs the best.
Okay, with that, I would like to say, Klaus, thank you very much for the presentation today, and that concludes our Park Optimizer webinar. And we wish you all a nice evening or a nice day, and any questions you can contact us at info@windsim.com.